When an inductor is first connected to a voltage source, there is indeed an initial high current. Your understanding of this phenomenon is accurate. Initially, there is no current flowing and consequently no magnetic field established within the inductor. Faraday's law of induction dictates that a changing magnetic field will induce a counter-electromotive force, often abbreviated as cemf, within the inductor. This cemf opposes the flow of current, causing the current to increase gradually rather than instantaneously. The initial high current arises because, at the very instant the circuit is closed, there is no opposing cemf present. The magnetic field has not yet had time to develop. The time constant, represented by the formula T equals L divided by R, where L is the inductance and R is the resistance, is crucial in understanding this behavior. The time constant determines how quickly the current in the inductor reaches approximately 63.2% of its final steady-state value. In the context of a transformer, the resistance is typically relatively low while the inductance is comparatively high. This combination results in a short time constant. The consequence of a small time constant is that the current increases extremely rapidly to its ultimate value. The initial high current is therefore only present for a very brief duration. To elaborate, consider the following scenario. When a direct current, or DC, voltage source is applied to an inductor, the current does not jump immediately to its maximum value, which would be the voltage divided by the resistance according to Ohm's law. Instead, the current increases gradually over time. This is due to the inductor's opposition to changes in current, a property stemming from its ability to generate a cemf. This cemf acts as a voltage source in the opposite direction to the applied voltage, effectively reducing the net voltage driving the current. As the current increases, the magnetic field around the inductor also increases. This changing magnetic field is what induces the cemf. The magnitude of the cemf is proportional to the rate of change of the current. The faster the current tries to change, the larger the cemf becomes, thus resisting the change even more strongly. The mathematical relationship governing this is expressed by the equation voltage equals L multiplied by d divided by dt, where voltage is the induced voltage, L is the inductance in Henrys, d is the change in current, and dt is the change in time. The time constant, T equals L divided by R, provides a measure of how long it takes for the current to reach a certain percentage of its final value. After one time constant, the current reaches approximately 63.2% of its final value. After two time constants, it reaches about 86.5%, and after 5 time constants, it is considered to have reached its final steady-state value for practical purposes. In a transformer, the situation is similar, but the parameters are often different. The primary winding of a transformer has a certain inductance and resistance. When voltage is applied to the primary winding, the current will initially rise rapidly, limited by the inductance and resistance. However, the mutual inductance between the primary and secondary windings also plays a significant role. As the current in the primary winding changes, it induces a voltage in the secondary winding, which can then drive a current through the load connected to the secondary. The behavior of the transformer is more complex than that of a simpler inductor because of this interaction between the windings. Now let's delve deeper into the concept of the time constant and its implications. The time constant is a fundamental parameter that characterizes the transient response of an inductor circuit. It tells us how quickly the current in the inductor will respond to a change in voltage. A small time constant indicates a fast response, while a large time constant indicates a slow response. The time constant is directly proportional to the inductance and inversely proportional to the resistance. This means that increasing the inductance will increase the time constant, while increasing the resistance will decrease the time constant. This makes sense intuitively. A larger inductance means that the inductor has a greater ability to store energy in its magnetic field, and therefore it will take longer for the current to change. A larger resistance means that there is more opposition to the current flow, and therefore the current will change more quickly. In a transformer, the inductance is determined by the number of turns in the winding, the core material, and the geometry of the core. The resistance is determined by the wire gauge, the length of the wire, and the material of the wire. By carefully selecting these parameters, the designer can control the time constant of the transformer. Now consider what happens when a transformer is first energized. When the voltage is initially applied to the primary winding, there is a surge of current. This is because the inductor initially opposes any change in current. As the current begins to flow, it creates a magnetic field, which in turn induces a voltage in the secondary winding. This voltage drives current through the load connected to the secondary winding. The amount of current that flows through the load depends on the impedance of the load. If the load is a low impedance, then a large current will flow. If the load is a high impedance, then a small current will flow. The transformer's primary inductance, secondary inductance, and mutual inductance govern the voltage and current relationships between the primary and secondary windings. These inductances are frequency dependent and contribute to the transformer's impedance. Inrush current is a phenomenon that occurs when a transformer is initially energized. It is characterized by a high peak current that can be several times the normal operating current. This inrush current is caused by the fact that the magnetic core of the transformer is not yet magnetized. When the voltage is first applied, the core tries to magnetize, and this requires a large amount of current. The inrush current can cause problems for the electrical system, such as tripping circuit breakers and damaging equipment. To mitigate inrush current, several techniques can be employed, such as using pre-insertion resistors, controlled switching, and specialized transformer designs. Understanding these concepts is crucial for designing and operating transformers effectively. Now let's consider some practical examples. Firstly, imagine a small signal transformer used in an audio amplifier. These transformers typically have relatively small inductance values and operate at audio frequencies. The time constant is small, allowing for rapid changes in current to accurately reproduce the audio signal. Secondly, consider a large power transformer used in a substation. These transformers have very large inductance values and operate at power line frequencies, typically 50 or 60 Hz. The time constant is significantly larger compared to the audio transformer. In such applications, the rate of change of current is slower due to the large inductance in cemf. The initial surge current can be substantial, necessitating careful design and protection measures. Thirdly, let's examine a scenario involving a flyback converter, a type of switching power supply that utilizes an inductor to store energy. During the switch-on phase, the inductor current increases linearly, storing energy in the magnetic field. During the switch-off phase, the stored energy is released to the output capacitor. The rate of current change during both phases is governed by the inductor's time constant and the applied voltage. Understanding the interplay of inductance, resistance, and time constant is critical for designing efficient and stable flyback converters. Consider the effects of core material on the inductor's behavior. The core material significantly impacts the inductance value and the magnetic properties of the inductor. Air core inductors have relatively low inductance values and are suitable for high-frequency applications where core losses need to be minimized. Ferrite core inductors offer higher inductance values compared to air core inductors and are widely used in various electronic circuits. However, ferrite cores exhibit core losses at higher frequencies. Iron core inductors provide even higher inductance values and are commonly used in power applications. However, iron cores are susceptible to saturation and exhibit higher core losses at high frequencies. The choice of core material depends on the specific application requirements, considering factors such as inductance value, frequency range, and core losses. Furthermore, temperature affects the inductor's behavior. The inductance value and the resistance of the winding wire can change with temperature. Typically, the inductance decreases slightly with increasing temperature, while the resistance increases with increasing temperature. These temperature variations can affect the performance of circuits containing inductors, especially in temperature-sensitive applications. Therefore, it is essential to consider the temperature coefficient of the inductor when designing circuits that operate over a wide temperature range. Also, consider the effects of parasitic capacitance. In addition to inductance and resistance, real-world inductors exhibit parasitic capacitance due to the proximity of the winding turns. This parasitic capacitance can resonate with the inductance at high frequencies, leading to unwanted effects such as ringing and instability. To minimize parasitic capacitance, techniques such as using spaced windings, minimizing the number of winding layers, and employing special winding configurations can be used. Consider the effects of skin effect. At high frequencies, the current tends to flow mainly on the surface of the conductor, a phenomenon known as the skin effect. This reduces the effective cross-sectional area of the conductor and increases the resistance. The skin depth, which is the depth at which the current density decreases to 1/e of its value at the surface, decreases with increasing frequency. To mitigate skin effect, conductors with a large surface area, such as Litz wire or flat conductors, can be used. In addition, consider the effects of proximity effect. The proximity effect is another phenomenon that occurs at high frequencies where the current distribution in a conductor is affected by the presence of nearby conductors. This can lead to increased resistance and losses. The proximity effect is more pronounced when the conductors are closely spaced and when the frequency is high. To minimize proximity effect, conductors can be spaced further apart or winding techniques that reduce the proximity effect can be employed. Now, let's discuss the implications of the initial high current in transformers for protection devices such as fuses and circuit breakers. The inrush current can be several times the normal operating current, as we previously discussed. If the protection device is not sized appropriately, it can trip unnecessarily during the initial energization of the transformer. To avoid this, it is common practice to use slow-blow fuses or circuit breakers with a higher instantaneous trip setting. These devices can withstand the short-duration inrush current without tripping, while still providing protection against sustained overloads and short circuits. Also, consider the importance of proper grounding in transformer installations. Proper grounding is essential for safety and for ensuring the reliable operation of the transformer. The transformer's core and enclosure should be grounded to provide a low impedance path for fault currents. This helps to prevent dangerous voltage buildup and reduces the risk of electric shock. In addition, the secondary winding of the transformer should be grounded to establish a reference potential and to prevent voltage imbalances. Furthermore, let's discuss the different types of transformers and their applications. Transformers can be broadly classified into two main types: power transformers and signal transformers. Power transformers are used to step up or step down voltages in power distribution systems. They are typically large and robust, and they are designed to handle high currents and voltages. Signal transformers are used to couple signals between circuits and to provide impedance matching. They are typically smaller and more delicate than power transformers. And let's consider autotransformers. Autotransformers are a type of transformer that has only one winding. A portion of the winding is used as both the primary and the secondary. Autotransformers are typically smaller and less expensive than conventional transformers. However, they do not provide electrical isolation between the primary and secondary circuits. Consider variable transformers. Variable transformers, also known as variacs, are autotransformers with a tap that can be moved along the winding to adjust the output voltage. Variable transformers are commonly used in laboratories and industrial settings to provide a variable voltage source. Additionally, let's discuss isolation transformers. Isolation transformers are transformers that provide electrical isolation between the primary and secondary circuits. They are used to protect equipment and personnel from electrical shock. Isolation transformers are commonly used in medical equipment and in other applications where safety is critical. Also, consider instrument transformers. Instrument transformers are used to measure high voltages and currents. They are typically used in power systems to provide accurate measurements for metering and protection purposes. Instrument transformers include current transformers, which measure current, and potential transformers, which measure voltage. The current transformer reduces a high current to a lower value, typically 5 amps, that can be safely measured by a meter. The potential transformer reduces a high voltage to a lower value, typically 120 volts, that can be safely measured by a meter. Regarding three-phase transformers, these transformers are used in three-phase power systems to step up or step down voltages. They are typically larger and more complex than single-phase transformers. Three-phase transformers can be connected in a variety of configurations, such as delta-delta, delta-Y, Y-delta, and Y-Y. The choice of connection depends on the specific application requirements. The turns ratio of a transformer is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. The turns ratio determines the voltage transformation ratio of the transformer. For example, if a transformer has a turns ratio of 10:1, then the secondary voltage will be 1/10 of the primary voltage. Transformer efficiency is the ratio of the output power to the input power. Transformers are typically very efficient, with efficiencies ranging from 95% to 99%. Transformer losses are the power losses that occur in the transformer due to factors such as core losses, copper losses, and stray losses. Core losses are caused by hysteresis and eddy currents in the magnetic core. Copper losses are caused by the resistance of the winding wires. Stray losses are caused by leakage flux and other factors. Transformer regulation is the change in the secondary voltage from no load to full load conditions. Transformer regulation is typically expressed as a percentage of the no load voltage. A lower transformer regulation indicates a more stable secondary voltage. Let's not forget about transformer cooling. Transformers generate heat due to the losses in the core and windings. This heat must be dissipated to prevent the transformer from overheating and failing. Transformers can be cooled by a variety of methods, such as air cooling, oil cooling, and water cooling. Air-cooled transformers are typically used for smaller transformers. Oil-cooled transformers are used for larger transformers. The oil provides insulation and also helps to dissipate heat. Water-cooled transformers are used for very large transformers. Transformer maintenance is essential for ensuring the reliable operation of transformers. Regular maintenance should include inspecting the transformer for any signs of damage, such as leaks, cracks, or corrosion. The oil level should be checked and the oil should be tested for contamination. The bushing should be cleaned and inspected for any signs of damage. The connections should be tightened and the grounding system should be inspected. Transformer testing is performed to verify that the transformer is operating properly and to identify any potential problems. Transformer testing can include insulation resistance tests, turns ratio tests, polarity tests, and impedance tests. Insulation resistance tests measure the resistance of the insulation between the windings and the core. Turns ratio tests verify the turns ratio of the transformer. Polarity tests verify the polarity of the transformer windings. Impedance tests measure the impedance of the transformer windings. And let's talk about transformer standards. Transformers are designed and manufactured to meet a variety of standards. These standards specify the requirements for transformer performance, safety, and reliability. Some common transformer standards include those from the Institute of Electrical and Electronics Engineers, or i.e. the American National Standards Institute, or ANSI, and the International Electrotechnical Commission, or IC. Now, let's briefly cover some common transformer failures. Common transformer failures include winding failures, core failures, and bushing failures. Winding failures can be caused by overloads, short circuits, or insulation breakdown. Core failures can be caused by overheating, overexcitation, or mechanical damage. Bushing failures can be caused by contamination, cracking, or a flashover. To wrap things up, remember that understanding the initial high current in transformers, along with the underlying principles of inductance, resistance, time constants, and cemf, is crucial for anyone working with electrical circuits and power systems. This knowledge enables informed design, operation, and maintenance practices, ensuring the reliable and safe use of these essential components.